Hello, we're going to look at volcanoes and some mountain building. And, if you look along the Cascades, we've got a whole mountain range, and many of those mountains are actually volcanoes. You've got Mount St. Helens, Mount Rainier, Mount Shasta, but they continue all the way down along the coast of the Americas, all the way into South America and Chile and Mexico. All of those places have active volcanoes and dormant volcanoes that used to be active. But back in March 3rd, 2015, Vilsari volcano in southern Chile erupted, spewing ash and lava 1,000 meters or 330 feet into the air. And this isn't the first time this volcano's erupted. But what's interesting is when you have a mountain erupting, you can have the normal magma coming down, you can have ash, you can have all of that. But if an ash erupts and it happens to do it at night, there's so much friction that it creates static electricity. And this isn't a thunderstorm. This is the volcanic ash generating lightning. And here's more, and you can see the colors. And as long as you're not in danger, it's beautiful. If you want to be a volcanologist, be prepared to go and climb in beautiful places around the earth that are remote and hard to get to. But boy, is the scenery worthwhile, as long as you stay out of the blast zone. This was just a little video of it. I'm not going to watch the whole thing. It's in the notes if you want to go watch the rest of it. It's only a minute or so long, but this was that eruption happening. You can actually see some of the lightning in the ash clouds as it's going. So what you're going to do is, after you've looked at this, we're going to look at different types of volcanoes. So a composite, a stratocone, a cinder cone, a shield cone. So let's take a really quick look at this. This is a cinder cone. It's really steep, okay? This would be really flat. That's our shield volcano. So this is like Mount Fuji. So this is really in Hawaii. Hawaii is a shield volcano. So you've got really runny lava coming out that spreads for long periods, creating a flat dome. Where if you have a cinder cone volcano, it's really sticky and it can build up really steep sides. Now, interesting, a shield volcano is a combination of both. It can have the really sticky eruption that makes it tall, and then it can be interspersed with runny lava flows where you get it's definitely taller than a shield volcano, but it's not nearly as tall as a cinder cone. So it spreads out, but it does get some height. So composite volcanoes, stratocone volcanoes, are actually a combination of a shield and a cinder cone. It has two different types of magma. Cinder cones have really sticky magma, and shield volcanoes have really runny, smooth lavas. And here's some pictures that you'll go ahead and try. And this, by the way, is a blown out center of a volcano. You get a big crater lake. So let's look at some magma and how it forms. Viscosity is what determines how far magma will flow. This is obviously really runny magma. This is from Hawaii, and you get this ropey. There's two different terms. Hawaiians have many terms for lava. You've got a'a and pahoehoe. A'a hurts your feet. Pahoehoe is like, ooh, nice and smooth. It's not going to kill your feet. And these are windows, places where the magma the lava has actually hardened on the top, but you get these tubes going underneath, and sometimes you can get little windows into it. This is just gases coming out, and you get a skin forming on top, and it creates this interesting effects. You can also have volcanoes that erupt high into the air. That's more like what you'd see in the Mid-Atlantic Ridge along Iceland, which you saw in the video the other day, or you're about to see today, I guess, sorry. And you can have these lava channels running out. And they can run for miles before they completely harden. All right. So what causes a volcano? Well, you have to have magma. You have to have molten material coming up. So you can have, we've talked about this before, you can have a hot spot, or you can have a subduction zone volcano where you're getting subduction, and this gaseous organic material creates lower viscosity, and it wants to heat and rise up, and that's our Mount Shasta, our Mount Rainier, our Mount St. Helens. And you can also have obviously the Mid-Atlantic Ridge, where we have rifting happening, where we have tension. The plates are being pulled apart by convection currents. So those are the three main types. You can have subduction, you can have rifting, and you can have a hotspot. Hawaii is a hotspot volcano. Yellowstone is a supervolcano, and it's a hot spot volcano. And as you'll notice from that video, as you watched it, it moves along, and we've actually had multiple different volcanoes. So how do we predict the eruption of an earthquake? Well, often we get small, measurable earthquakes before an eruption happens. You can also measure the slope, so the angle. So sometimes it starts to bulge out, and we have a tilt meter that literally tells us that the volcano is starting to swell. The magma chamber is filling. We can also measure from the vents volcanic gases coming out, and we have the ability from orbit to measure the temperature. This is the inside of Yellowstone.
Recently, scientists have collected new data, giving them a better picture of Yellowstone's underground plumbing. Right beneath the caldera from the last eruption sits the magma chamber. And it's fed by a plume of magma stretching down 465 miles northwest into Montana. It's mostly solid rock with the potential to liquefy. And scientists are closely monitoring it. Magma, or molten rock, is rising through the plume into the magma chamber at 2 inches a year.
There's no reason for it to stop, although it might come in spurts. Our images show wider parts and narrower parts, so it's like slugs of material that are flowing in a sewer line. And this restless Yellowstone caldera is truly living, breathing, and every once in a while it bursts.
The danger is if the plume starts liquefying and moving up at a faster rate.
Natural systems can throw us a lot of curveballs. A lot of things can happen that we're not really ready for.
Scientist Jake Lowenstern is looking for a pattern connecting the supervolcano today and its 3 prior major eruptions. 2.1 million years ago, 1.3 million years ago, and 640,000 years ago.
In 2 of the really large eruptions at Yellowstone, so much material comes out, entire mountain ranges end up falling into the ground and essentially disappearing.
One 50-mile stretch of mountains simply disappeared by collapsing into the magma chamber. University of Toronto geologist John Westgate has tracked the ash from Yellowstone's prior eruptions.
It covered much of the United States. It occurs right out in the Pacific Ocean. It's even found in the Gulf of Mexico. Up in northeast Montana, there's a site that we're working on. The tephra is over 7 meters thick.
Tephra is what he said.
These eruptions are enormous. The amount of material erupted from them, huge.
When Mount St. Helens erupted in May 1980, it blew off one side of the mountain and triggered an avalanche of snow, mud, ash, and rock.
Pyroclastic flows can kill a lot of people.
The ash landed in 11 states and up into Canada. But that's nothing compared to the amount of ash from Yellowstone's last 3 major eruptions. In magnitude and volume, each one was far greater than Mount St. Helens. Today, there's little evidence of the supervolcano's violent past. The 50 by 30 mile caldera from the last eruption was covered by lava and ash and smoothed over by glaciers. Forests now conceal the scars.
Okay, so to be a volcanologist, you need to want to go backpacking and hiking and rock climbing and have that be something, because if you're not interested in that, you do not want to be a volcanologist. And you want to be able to travel to beautiful places, and you like all those things, maybe this is something you'll be interested in. So remember, subduction zone, we have the plate coming underneath, it melts, it comes up, we get like Mount Shasta, Mount Rainier, Mount St. Helens, subduction zone volcanoes. We have mountain building, so as this happens, it can also cause rippling effects, and we'll watch something on the Rockies and see that that happened as well. Hotspot volcanoes would be like Hawaii and Mount St. Helens. You did the Hawaii worksheet, so you saw the progression as Hawaii, the chains have moved off of the hotspot, creating new islands. Mountain building and folds. So you can get folds from this compression. Compression can literally create that anticline and syncline that you see here, and you can get waves of folded mountains, and they're beautiful if you get a chance to go see. Continental rifting is like the Mid-Atlantic Ridge, where all of this comes apart, and if we look here, sorry, that's a question. This, as it's pulled apart, we get like Iceland growing, and we're getting farther away. There's some questions in here that I'll be putting in. And as always, I've got the notes in Schoology that I used, and they're available to you. But you're going to want to do this video's questions because the ones in Schoology are simply for reference. I am not scoring those.